Good morning, folks. How are you today? We are in week number 6, and this Friday would have been lab number 6. This lab, instead of lab number 6, we are going to have midterm test number 1. It is going to cover lecture content up to this past Wednesday, which was lecture 14, Wednesday, February 24th. It'll cover online quizzes 1 through 9. You might want to see again test number 1 equations that I have posted on my courses. You should know what each symbol means. No help would be provided during the test. The test is closed book, closed notes. I trust you. Ordinarily, if it had been a normal semester, you would have been taking the test using pen or pencil. I would have given you a hard copy of the test, and the only thing you would have is test 1 equations sheet plus your calculator. Instead, this Friday, March 5th, we are going to have a synchronous test during the class period 125 to 215, 50 minutes. So it is online because we are not having any in-person classes. It is synchronous, so that means you must take the test during this time period. It is limited time. You must finish the test in the 50 minutes. There are 34 multiple choice questions, same or similar to your online quizzes. We are going to have a review class for the midterm test on Wednesday, this coming Wednesday, which is March 3rd. It is a synchronous Zoom meeting. I posted it on my courses. It is from 125 to 215 during the class period. I would really appreciate if you could have your camera on, and we are going to talk about uh, what are the things that are going to be covered on midterm test number 1. So we started with root of a nonlinear equations. We covered many methods. And then following that, we looked at integer and floating point system in computers. We talked about errors, correct decimal digits, significant digits. Then I gave you an introduction to matrix algebra. And then we covered methods to solve a system of linear equations. So this Wednesday, when you come for the Zoom meeting, I sent you an email and I've posted the same email on my courses. So please come to the review session uh, with whatever topics you want me to review, as well as if you have any specific questions from class examples or online quizzes. Um, Please make sure you have identified them and have some kind of a detail. I may not be able to bring the example quickly online. Okay. I also want to encourage you to watch this PBS episode titled Search for Life on Mars. You may remember I told you I have a personal uh, interest in this when I came to this country 45 years ago. Uh, US had just uh, shot to the space Voyager 1 and 2, and they are still in operation. And just a week ago, you might have seen on TV that we were able to land Mars Perseverance, a short name Percy. Uh, So I really would like to encourage you to watch the PBS video titled "Search for Life on Mars." As you can imagine, this particular rover has extensive use of numerical methods to process data that it is collecting from various sensors. So stuff that you are going to be learning in this course is very much integral to performance of Percy. So I hope you watch it and I hope you enjoy the video. Our next topic is Taylor series. I am sure you have come across Taylor series previously. If I had to say, with the exception of linear system, this entire numerical method course is directly or indirectly connected to Taylor series. So what is Taylor series about? So what Taylor series is about, it says, let's suppose we have function of one variable x. And at a particular x value, we know something about this function. What do we know? We know the function value, first derivative, second derivative, and so on. And what we want to do is we want to predict what is the value of the function some distance away. So some distance h away. This is x plus h. So think of h as same as delta x. So then what Taylor series says is that f at x plus h is this function value. So first time I'm going to expand it. H times this derivative value, h squared by 2 factorial times the second derivative value, and so on. So you can see that this is a polynomial in H. And it is of course a infinite series. So the question is, for it to be practical, when do we stop? So which stop, let's say, after n terms. So we have a polynomial, we stop having n terms. And instead of saying this polynomial is h, which is what it is, I'm going to write it that it is a polynomial in x. What about the remaining terms? What we do is we say the remaining terms are all coupled in this error term called the remainder term. So this is our polynomial and this is our remainder. So what we do is we write remainder term, we say the next term is the largest of all, since if it is a converging series, that's what should happen. So next term to the nth term will be h to the power n plus 1 over n plus 1 factorial times the n plus 1th derivative, and we need to evaluate where this n plus 1th derivative is. And thing is, since this is kind of a total term, what we do is we say we will evaluate it at some zeta value. All we know about zeta is it belongs to range x and x plus h. Little later on, from a numerical analysis perspective, we will use this term will become our error bound. So we'll think in terms of this as our absolute error, which we will convert into error bound. Notice we do not need to know these derivatives explicitly. We just need to know their numerical values. This is what we are going to use here. Okay, before we move on, let's see its relation to what we have done so far. So you may remember we talked about your square root key on calculator. And I said square root key implements a form of Newton-Raphson method. And in Newton-Raphson method, what we had done was we started with a guess x, and then we computed delta x. And our delta x was function value at x, this guess, divided by derivative at that x. And then we said our new guess would be x plus this delta x, right? And to derive this, we had used a geometric argument. Now let's see how we will use Taylor series. So what Taylor series says is function at x plus h is function at x plus h times derivative at x. And we'll neglect rest of the terms. So we already have an old guess. And what we want to do is, remember, h is same as delta x. So we want to find delta x such that the next value of the function is 0, because that's what we are solving. We are solving fx is equal to 0. So we want this to become 0. If this becomes 0, then you can see h is minus fx over f prime x. And this is our delta x. So you can see we can derive Newton-Raphson method directly from Taylor series. Okay, let's do some examples. Let's suppose we are using Taylor series to evaluate sine of a function in your calculator. So you have sine x key in your calculator. So it uses a form of Taylor series. So what we have is we have function is sine of x. And let's say we are going to expand it to a polynomial of degree 2, n is equal to 2. And we are going to expand it about x is equal to 0. So our function is, of course, it's a great idea to make a table. Our first derivative is cosine x. Our second derivative is minus sine x. So this is what we need for our polynomial. For the remainder term, we will need the next derivative. So let's derive that too. Third derivative minus cosine x. So let's evaluate this at x is equal to 0, because we are expanding Taylor series about x is equal to 0. So this would be 0, this would be equal to 1, this would be equal to 0. So our second degree polynomial, remember, was fx plus h time f prime x plus h square by 2 factorial times second derivative of x. So let's substitute values. So fx is 0, h times first derivative is 1, and second derivative is 0. So our approximation therefore is P2 is H. Let's look at the remainder term. So it'll be the next term here, H cubed over 3 factorial times third derivative at zeta. Okay. So what we want to do is we want to find its largest magnitude when zeta goes from 0 to 0 plus h. So we know cosine is maximum at 0. So its largest magnitude would be equal to 1. So therefore we have R2 is h cubed over 6. So that will be our absolute error bound. So this is our approximation, and this is our absolute error bound. So what we are saying is sine at 0 plus h is approximately h plus minus h cubed over 6. Okay. So the question to ask is, what range 0 to h we will have 4 correct decimal digits using our P2 approximation, second degree approximation. So remember we had sine expanded about 0 was h plus minus h cubed over 6. So this is our P2, this is our R2. So what we want is we want R2, which is our absolute error bound, to be less than equal to 0.5 times 10 to the minus 4 CDD. So from here we can calculate that h must be less than equal to 0.5 10 to the minus 4 times 6, and then we take cube root. So we'll get 0.067, and of course our units are radians. So let's check. Let's suppose h is 0.05 radians. So well within this range. So we should get 4 correct decimal digits. Okay, so let's see, sine of 0.05 radians is, if you use your calculator, you will get 0.04998. If you use P2, our second degree approximation, remember our P2 is h. So h is 0.05. So let's show all those digits there. Okay. So what is our absolute error bound? After absolute error bound is R2, which is h cube over 6. H cube over 6, 0.05 cube over 6 is 0.12343, right? So this is 0.3 times 10 to the minus 4. All right, what is our actual error? Our actual error is 0.05, which is our approximation, minus 0.04998. We'll take magnitude, and you can see this is 0.2 times 10 to the minus 4. So our actual error is less than absolute error bound, and this is what we expect. And you can see we have 1, 2, 3, 4 digits correct when we round it up. Okay, let's do another example. This time, let's take the function sine of x. So we'll take function is sine of x, cosine of x. And again, we are going to use second degree polynomial about x is equal to 0. So our function is cosine x. We need first derivative. We need second derivative. And so this is good for n is equal to 2. So for remainder term, we'll need third derivative, which will be plus sine of x. Okay. At x is equal to 0, this is 1, this is 0, this is negative 1. So this is what we are going to use for P2. So our P2 is going to be 1 plus h times 0 plus h square over 2 factorial times negative 1. So we'll get P2 is 1 minus h square over 2. Okay, let's look at what is R2. R2 would be h cube over 3 factorial times third derivative, which is sine of x, so it will become sine of zeta. Zeta is from 0 to h. So the largest value this would have in this range is when zeta is h. So this would be sine of h. So our R2 would be h cube times sine of h divided by 6. Okay. So let's pose the same question. So our approximation n is equal to 2. We approximated cosine about 0. Our second degree polynomial was 1 minus h square over 2. So this is our P2. And this is our R2. So what is the range? That we can get 4 CDD in our approximation. So all we have to do is look at R2, which is h cubed times sine of h over 6. Now this, when h is small, we know, we just did this, sine h is approximately h. So we can write this as h to the power 4 over 6. So if we want 4 correct decimal digits, we want this to be less than 0.5 times 10 to the minus 4. This would imply that h is less than equal to, so we do this calculation, 6 times 0.5 times 10 to the minus 4, and then take power 1 divided by 4. We take 1/4 of the root, and we will get 0.131 radians. Right? I don't round up here because we want to be conservative. Okay? So it is good to 0.131. Let's do the same here. This is a much larger range, notice, than sine range. Let's consider h is 0.05 radians. So our true value is cosine of h, 0.05 radians, and we will get 0.99875 on and on. Let's see our approximation, which is P2, which is 1 minus h square over 2. So we substitute it, I get 0.99875. Okay, so I match first 5 decimal digits. Let's see what is R2. R2 was h to the power 4 over 6. So this is 1 times 10 to the minus 6. So this is our absolute error bound. Let's see our actual error. So if I put in my calculator cosine h and P2 so that I don't lose any significance by handwriting it, I'll get 3 times 10 to the minus 7. So this, of course, actual error is less than the error bound, right? It's 1/3 almost, 1/3 the error bound. Let's do one more example. So let's say this time our function is 1 over 1 plus x. This time we'll go up to, let's say, n is equal to 3. But we'll still do it about x is equal to 0. So as before, we create our table. Our function is, it's easier to write it as 1 plus x to the power 1 minus 1, because then taking derivatives would be easy. So first derivative, minus 1 plus x minus 2. Second derivative, plus 2, 1 plus x minus 3. Third derivative, minus 6, 1 plus x minus 4. So this is what we need for our third degree polynomial up to third derivative. Then for R3, we will need fourth derivative. So it'll become plus 24, 1 plus x to minus 5. Okay, let's calculate this at x is equal to 0. So this is 1 minus 1 plus 2 minus 6. So our P3 would be 1 plus h times negative 1 plus h square over 2 times positive 2 plus h cube over 6 times negative 6. So we will get P3 is 1 minus h plus h square minus h cube. Right? Okay, let's do R3. R3 would be, so we went up to h cube, so we'll go h to the power 4 over 4 factorial times 24 times 1 over 1 plus zeta to the power 5. So that is going to be our error bound. You can see 24 and 4 factorial cancel out. So we will just get h to the power 4 over 1 plus zeta to the power 5. Now to analyze it, let's plot. So this is x, which is same as zeta. And let's say this is our R3. Remember, R3 is h to the power 4 over 1 plus zeta to the power 5. Right? So we just need to look at this variation. So you can see when zeta is positive, when zeta is greater than 0, as zeta increases, R3 is going to decrease. Right? So it be some value here, it is going to decrease. And we are interested in magnitude only, remember. But if zeta is negative and we increase its magnitude, this quantity will become small and this is increased. So this curve would look like this. So in the positive range, largest value is at 0. So when zeta is equal to is positive, our error bound R3 is going to be h to the power 4 exactly. Right? On the other hand, if zeta is negative, then the largest value would be whatever this zeta value is. So when zeta is negative, R3 would be h to the power 4 divided by 1 plus zeta to the power 5. But of course, zeta can be no more than h. So you substitute h to the power 4 over 1 plus h to the power 5. So this is what we will have. Now in your next quiz, you're going to find a number of questions. And of course, they are going to be related. And you have to be careful. So I may start with the series and then I may give you a function, ask you to start with the series. Next question would be find the polynomial. Next might be find this remainder term. And next might be how many digits and so on and so forth. So you just need to be careful. Yes, all the questions, 4 or 5 questions would be interrelated, but I'm breaking up a big problem into small parts. So be patient, be careful, try to understand what the problem is about.